Good morning, everyone, and welcome to the first BASH event of 2021. So I have quit out of Slack. Updates have been disabled on this machine. The cat is outside, and the windows are secured against pigeons. So hopefully we are good to go. Yeah. So we have three excellent talks for you today, exploring the Rust language. So thank you in advance to our speakers for volunteering and to yourselves for your patronage. So a few announcements before we start in. As always, if you have a suggestion for a BASH event, or if you would like to present yourself, please let us know. Yeah. Then you may have heard that IntelliJ is celebrating its 20th birthday, and there's an IntelliJ conference going on right now. So they've had some wonderful presentations on debugging and power use of the IDE and Spring Boot. You know, so if you've any interest in Java development and IntelliJ, that's worth a look. And speaking of Java, our next BASH will be on the 26th March with the theme of modern JVM development. So just like this event, we've got three excellent speakers lined up, and we'll be announcing the details next week. So we'll be opening that up. So please keep an eye out for that. So that's it. That's all the announcements. So without further ado, I would like to welcome Richard to the stage to give his first talk. So that's going to be an introductory tour of the Rust language. So over to you, Richard.
Thanks, Garth. Okay, so as Garth was saying, kicking off this Dev Bash with just an introduction to Rust. My name's Richard Gibson, and I've been. Oh, have we got our desktop shared? I think we're all good now. Apologies, sorry. So yes, I work for a company called TextLabs.io, and we're going to be going through just a quick beginner's introductory to Rust. So I picked up Rust last year. A language that's sort of been on a list I wanted to explore for quite some time, and had heard a lot of good reports from people that I knew that programmed with in the past. And what I was a bit surprised whenever I started looking into it, actually for this talk, I realized that has on the Stack Overflow surveys, it has come up 5 years in a row as the most loved language. So I thought it would be a good thing to sort of explore why and what was good about it. So I'm going to talk a little bit about the language, but also a bit about the ecosystem as well. So a little bit about Rust. So it's primarily a systems programming language, which usually means it's something that's going to be run rather than being user-facing or an application-type program. It's going to be run at quite a low level. So yeah, it started at Mozilla. It's used extensively in companies like Amazon, Google, and Microsoft. And you've been using it more than likely if you've used something like Firefox. Deno, the new implementation of Node.js, also is written in Rust. Or if you use something like AWS Lambda, their VM, it's called Firecracker, is also written in Rust. So it's used quite a lot in the industry already. It's a compiled language, but it's compiled down to binary. So it means that it's able to be executed natively without a runtime. And there's no garbage collector there. So, and because of these things, it also is able to give a performance that's on par with C. It's also it's a strong statically typed language, like say something like Java, Scala, or C++. And the language itself is it's an imperative language, so it's mostly functions and data, just with data. But it has a number of functional and object-oriented features included in it as well, which makes it very nice to use. So the other thing that I guess it gives it a lot of press is the way that the compiler or the type system is able to ensure give a number of guarantees that weren't able to get with other languages where automatic GC is not there and not available. So one of the first things that it is able to do is that the compiler is able to guarantee that if a Rust program can compile, that it has got it's got correct memory or allocation or deallocation. So there's no chance of something like trying to free memory when it already has been freed, or leaving memory with allocated when forgetting to deallocate it. There's no surprises with types. And what I mean by that is that if I have a type that's supposed to be a string, I know that it's not going to be null. I know that if I call a function that's going to return a string, it's not going to throw an exception. The type, if you are going to get those sort of things, it has to be encoded in the type signature, which I'll explain a little bit more about later on. The other thing the compiler can guarantee is there's no race conditions across threads. So again, incredibly powerful sort of things to be able to eliminate bugs like that from your runtime. One of the other really nice things I've found when we were talking about how a language is loved, after writing a number of different languages, one of the things that I find you get used to is not just what the features of the language are, but what the community is like as well, and the ethos of the language, of the community. So in the Rust community, Rust itself is stewarded by people called the Rust Foundation, which is community-driven, but it's got industry support there. They have an open RFC process. You can go along and watch the RFCs being considered. It's all very open. Really good tooling around documentation. So the libraries that they have are incredibly well documented. Lots of free books and learning resources that are available for anyone, and a very inclusive culture. So stuff that would traditionally be seen as, a closed sort of subject or something for the experts, they try to make as open and able for anyone to really to get into and to try out. Okay, so some of the tooling that I really enjoyed as I've been picking up Rust. So one of the first ones you'll see is Cargo. So it's their standard build tool with a package manager, and they've got a linter in there as well, which is able to really help you with writing good idiomatic code. Rust formatter, so really nice. You don't have to go bike shed over 2 spaces or 4. You can just go in and configure it, and everyone works to the same standards. The Rust doc, which is a great documentation tool, similar to stuff like Java and doc or any of those other sort of things. But one of the cool things you can do with it is you can embed a piece of code inside your documentation, and it will compile the code in your documentation. So what that means is that if your library changes, you make API changes and you don't update your documentation, your build will fail, and you'll be able to catch those and keep your documentation up to date. Find excellent editor support, so you can use VS Code or Vim or Emacs or IntelliJ IDEA. They all seem to work really well. And one of the other things that took me a while to realize is that the compiler actually gives out sane error messages that guide even beginners when you're starting with Rust. So I'll give a few examples later on here too. Okay, so if I want to set up really simply, if I'm a Mac OS or Linux, I can just go and grab a tool called RustUp, which looks after your versioning of Rust that you're working with. And then, sorry, apologies for this. But once you've got that, you're ready to go with Rust. You're installed. And the next thing you want to do is you can use Cargo, which is your default build tool installed with Rust. And you can create a new project just using Cargo new, your project name. We've got here bin --bin for an application, lib for a library. And then once you go into the directory and build it, you'll go off and fetch any dependencies that you've specified from centralized repository. And you can see that we're able to run this. In this case, we just run it in a dev mode, but you can also run it as a release. It takes a little bit more time to compile, but more optimized. Or if you want, we can just use Cargo to run this, and it will just run again. So sounds all really simple sort of stuff, but as a system, if you've been used to using C or C++, to have this up and running in a few minutes is just an incredible tools to have. So I guess if you were coming from, say, it's probably very, very similar if you're coming from a JavaScript or another more modern language, you'd see these things just as easy to set up. Other useful stuff that you have in Cargo, you have tests that you can go and compile your unit or integration tests. You can go fetch dependencies to work offline. Go get a dependency tree, search for packages in your repository, or format your code, and then also help commands as well. So really, as I said, nice sort of de facto things you'll see in a modern language. Okay. Also, with the package management for it, you can go off, as I said, and grab something from a central repository like crates.io, or you can use a Git repo or local path to go and grab the actual code itself and build as well. So it's the the configuration of this is really nice and simple to set up. And then, as I said, with your comments in your Rust doc, you can also that they become documentation. If you're going to actually create your own library, the comments you have in Rust doc then get published up to the registry itself and become easy to be searched by users. Okay, just a real quick tour of the Rust language. So I'll start off standard stuff, just initializing variables. As you can see here, very nice and easy. We're just assigning 1,000 to I here. And what it's doing is it's going to be implicit here. So it's not a dynamic language. It's going to implicitly make I an I32, which is a signed integer of 32 bits. Or we can also explicitly say what type we want to make it if we want to help give the compiler a hand, or if we want to do it for documentation. And in this case, any primitives like this, they're going to be assigned to the stack. But we can also do things like this with a box, where we can assign it to a heap as well. So in this case, we're assigning one to, we're creating an I32, but we're ensuring and enforcing that it's going to be assigned to the heap. And then just to say, this little star here is something that will actually go and copy the value from the heap, and then to do this operation. So it comes with Rust comes with default immutability as well. So when we say let j equals 1,000, there's no way to change j at this point. And without, if we want to change something like this, we actually have to define the variable as mutable. So this is what's happening here. We say let mut I equals 1,000. And as you can see, whenever we run this against, we try to increment j, the compiler gives us one of these nice helpful messages telling us that there's a problem trying to, what j was already been assigned as 1,000. We can't reassign it with this +1. And it says something like, try making this mutable. It tells us what to write in here. This is something that you get in lots of other languages. Scala has it, and Kotlin, Java, so where you can place a final in front of it, or a val and a var. But usually that just makes the reference immutable. In Rust, if you say something, if you don't put a mut there for a structure, then not only is the reference immutable, but the structure itself also is immutable. So if you see here, we have these two vectors. It would be like a sizable array that's held on the heap. If we make it mutable here, we are able to push something to the vector. If we don't, then the vector is not able to be altered. We have guarantees that that will not change. And again, in this case, we're able to say, oh, a mutant vec is mutable. So everything, it's able to tell you exactly what the problem is, where it is, and what you should do with it. Just a little bit on the function syntax. Really simple sort of stuff, but we've got our fn as a prefix there to say that something's going to be a function. Again, sort of C-like, that we take in our parameters here of our curly braces. This is going to be our return type, which is an I32. We're going to take two I32s. In this case, we're just squaring the parameters and then adding and returning as a sum. One of the things that is a little bit more terse in the syntax is that if you have a semicolon, that's seen as a statement that's executed, and that the last line, if it has no semicolon, is what is going to be returned from the function. For something like a void function, we just don't bother putting anything at the end here. It will know that it's void. And in this case, we have 3 statements being executed. Okay, so ownership. This is how Rust deals with memory management. So this is the part that, as I say, gets a little bit of press, and is pretty tricky to come to terms with, but it is an incredible tool and very, very elegant in the way it works once you start to understand it. So with garbage collection, we always have to clean this up, or our machines will run out of memory. So usually there's 2 ways we do it: either explicitly through the code, where we're going to allocate and free memory once we're done with anything that we're using on the heap, or implicitly through a garbage collector whenever you have that in your runtime. So something like when you're using many languages that use garbage collectors. Rust uses another technique where what we're going to do is it enforces that memory is actually safe at compile time through this thing called ownership. And what happens here is that any variable that any data assigned to a variable is going to be cleaned up automatically when that variable goes out of scope. So yeah, and then the part that gets a little bit tricky is that whenever that data gets assigned to something else or needs to be read by another variable, that this compiler can start to complain. But the nice thing about this is that Rust views memory just as a resource, the same way as a file or a TCP connection. So whenever anything that's holding the file handle or the connection goes out of scope, that also gets cleaned up. There's no need to explicitly close things, or do something like a finally, try catch finally, or anything of that nature. So just to give an example here, in the code here, we're just assigning this data, which is a string called hello, to a variable s. Then we are saying let y equals s, which usually would mean y has another reference to the same string. But in Rust, what we're doing is, in the first case, s becomes the owner of the string. In the second case, what we've done is we've just actually transferred ownership over to y. And Rust will say that only one variable can own this piece of data. So once we call here, println to say hello world on s, well, we get an error saying that, no, you can't do this. Your ownership has been moved from s, is what it says here. You can see because of what's happened here, we're not able to print this, and we get an error. So what happens here? How can we fix this? Well, as I said, we have these rules of the ownership. Only one owner for a piece of data. Data is cleaned up when the owner goes out of scope, and an ownership can owner can transfer ownership to another of a piece of data. Or, in what we're going to show in a second, it can also lend it out to another variable. So how we fix this? Instead of saying y equals x, we can say y equals ampersand x. And what that does is that gives what's called a reference, or it's like a pointer. It's a read-only reference in this case. So y is now able to read the value and is able to assign it to s, or we're able to work on with s. Y does not have ownership of s. When y goes out of scope, the string does not get destroyed. Everything is good with this. And we can have as many of these references with ampersand as we want, as long as they're immutable, like these read-only references. We can also have a mutable reference, but there's only one ever is allowed. So this gives great safety in who is in control of memory, and lets the compiler understand when a piece of memory has been is able to be garbage collected. Also, in more complex things, Rust does have reference counting structures as well, like Swift or Java. So you can use these if you need to also. Okay, so back to the language features. Other things you might want to do, you can create a struct, which is similar to a class maybe in other languages, but it's just a data structure of a bit more complex with nested data types inside. In this case, we're creating a person, names, and age, all fairly straightforward stuff. Just to show as well, we don't have, it doesn't have a function, you can't create functions inside it, but we have another technique to do that. But we have this thing here, it's called a macro. So what I've been able to do is whenever I add this here, we're able to give a quality and some sort of debugging or two-string nature to person here if we add this extra little piece of code. We also have enumerations, which you have in lots of other languages. So, and the way that we can work with these is using something called a pattern match. So in this case, you can see we've created something, a primary color enumeration, and we can go through and say if it's red, we want to create an integer 1, otherwise 0. But the pattern matching is exhaustive. So if we miss one of these out, we know that it's going to, the compiler will let us know about this. It won't compile. So we know that we're always guaranteed an integer here. There's not going to be some sort of edge case scenario here. Also, enumerations are able to hold data. So in this case, this is something called an option. So if you're used to a functional background, this is something called an algebraic data type. So in this case, we have an enumeration called an option that will either be none, which is like an empty case, or it will contain something, and that something will be a type T, whatever the type option is. So that could be, so if an option of a string will contain some string. Another example of this is result. This is so option and result are stuff that are in the standard language, which I'm going to show in a second, or that is used extensively in the standard libraries. Result can either be something that is okay of type T, or something that is an error of type E. So it's your exception type. And again, we can pattern match it with these things. And you can see that when we're pattern matching, what's quite powerful is that if you're pattern matching on an option and there's something there, we can automatically extract I out of that option and use it. And the compiler will know that in this case, it's an I32 because we've got an option, O1 is an option of I32. So we know that I is going to be an I32 also. And again, the same if we were using that in a result. So if we have I, the compiler can understand what that is and use it from there. We also have this if let sort of syntax as well. So if I have a result and I want to know, if it's okay, then do something, we can use this as well, which is quite handy. Some of the other new syntax that they've put in here is this question mark syntax. So if you were wanting to combine a couple of options together, what this syntax is really doing is it's saying it gets an option and says question mark. And what it does is it says, if this contains something, then assign that something to I, and then also to J. And then we can work with I plus J, and then return it with a sum. If any of those are empty, it will immediately short circuit and would return a none. And then also the same with a result. If we were parsing something or doing something to get an integer, if it's successful, we'll get our integer, I or J, be able to work with it, and then get our result. Otherwise, we'll get our error. And again, if you're from a functional background like Scala or Haskell, this looks very, very similar to like a for comprehension or a do notation. Okay, so other parts of the language. So as I was saying, structs really are just data in Rust, but we do have ways to create methods for them. In this case, just as a nice syntax for us, that we'll create an impl for the struct, and then we're able to create these functions for that impl. And then as long as that's been imported, then we're able to work with those. So the very cool thing is that these don't have to be in the same file, that you can create these at another stage. And if you can see later on, so if I've created this variable called person here, I'm able to then access a person.toCSV, which is the method here. And notice also that the person itself is actually passed through as a reference called self, and we can go grab the name and age and then return a string with these being formatted. And then also we can actually create a mutable handle for self as well, and then go and increment its age. But again, this will only work if person itself is mutable. If that wasn't immutable, then engage would not compile. Okay, so the other thing that really was very lovely to use with Rust was this idea of shared behaviors, which is in most languages. So it'd be an interface in Java. It sort of looks at similar sort of way, or a trait in Scala or something like that. The actual implementation is something, again, that's taken more from something like Haskell. It's called a type class. So there's a common shared behavior called from strings, where you want to parse a string and return a result of some sort of object. Maybe it's an integer, maybe in this case it's a person. And so this is the implementation for person for this from string that we're using. It has these mandatory fields that you have to create, an error that's going to return, and this function called from string. And it will return a result of person or an error. And so what we can do is we can take, this is an implementation just to split CSV parse CSV string, grab, not a very safe way, but works for the example, the person grab the first part of the vector that's there and create a string for the name, parse the second part as an age, and then return this struct of a person. And as you can see, what then happens is that we can run something like Fred, 32.parse. Now this parse actually will not compile unless there is a from string instance for person in scope. So we know that we're going to, when we do this .parse, If we don't have this, if we don't have a way to actually parse it, the compiler will let us know all about it. And so in this case, this works with an OK Fred 32 person. And then if we don't have our if we don't have an integer here, it's going to fail and the error is returned. Other great language features I'd love to be able to talk about. It's, as I said before, it has a lot of safety around concurrency. The compiler is able to check if you're sharing anything across threads and make sure that you're doing it in a safe way. They have just released async await features, so it's very similar to Kotlin or TypeScript, JavaScript, in just doing parallel features. And then also they have a very, very powerful macro system that is able to be used for just pre-processing of code and hiding things away. And it's used extensively in Rust language itself as well. So as far as it being a loved language, as I said, really nice language to use, lots of features there, but lots of modern tools for system programmers that come almost out of the box, very, very simple to set up. We've got our memory safety and concurrency safety. So what I didn't also say is that those enumerations like option and result, they've no cost in them, so they're optimized away by the compiler, as opposed to something like Java where it'll be extra object allocations being used. Really thoughtful interoperability, which I think Chris is going to be talking about soon. So really easy to, there's a foreign function interface for using for other languages if you want to use Python to call Rust or Erlang or any of those sort of languages. And very easy to compile for multiple platforms also. And as I said, the active community makes it really nice, a nice experience to do as well, to use as well. Oh, so apologies for the link there, but yeah, I'll post this afterwards. But there are a number of resources I really liked. The Rust book is sort of the official book. You can get a print version, which I did actually, but it's free online. Rust by example, also good. There's a number of other ones with macros and asynchronous programming. All books in Rust are free and available. Great YouTube channel with lots of resources also. So yeah. Really enjoyed it. So there you go. Right. That's me.
Brilliant. Awesome. Thank you so much. That's a wonderful overview of the language. Rust was on my list of languages to look at after the languages I claim I already understand, but it's so that definitely looking forward to having a go at it now. So a few little questions as always. Are there any issues in platform portability, in terms of the build files or the code that you write, will it work equally well on different operating systems?
So it's probably one that Philip's going to be a lot better with. I haven't much experience with that. From what I've seen though, between the little tool that you're using there, Rust Up, and Cargo itself, you can add support for other platforms. Anything that's supported by LLVM, and then hopefully, as Philip's going to be talking about GCC, you can compile. So it's the quick and easy answer is you do one command with Rust Up, and then you add a new target when you're building in Cargo, and it takes care of the rest. I'm sure that there's probably a little bit more to it than that. And whenever you're using it really in anger, as I say, Philip and Chris can probably can say a lot more in that one. But yeah, the easy answer is a couple of commands, and away you go to write it to compile for iOS, Android, or a bunch of other things like that.
Excellent. Very good. Very good. And then in terms of the macros, I have to ask the question, are we talking C style, or are we talking Lisp style, or are we talking something in between?
So they're saying it is quite C style. They're really actually readable. So they're usable. They're hygienic, which means they don't leak out into your code. They're very self-contained that way as well. So they seem, I've read them, and there's been good reports of them, but yeah, it seems pretty good that way.
Fair enough, fair enough. Then are there any other built-in FP abstractions besides option? Do you have like a built-in either or anything like that?
So result will work pretty much as an either. I guess it's not just as abstract in that sort of either way of using. They have, other sort of entry-level stuff. They have Lambda support as well, obviously, and you can use map and flat map on certain structures. And you have a sort of like Java streams. You have an iterator and a collect that you can use on any sort of collection type objects as well. And yeah, so the type class abstraction, I showed you that from string, they actually end up using that for their memory just for dropping things and deallocating memory, and use it very extensively. Very cool stuff.
Cool, very good. And as somebody who has likes his Scala and likes his Kotlin and so on, just overall, how tempted were you? I mean, if you had a Rust opportunity tomorrow, would that attract you, or do you think it's just interesting?
No, definitely. Really enjoyed it. As I said, I don't mind fighting with compilers. I've done that plenty in other languages, so that I don't mind, because it makes me feel happy that I'm not going to see things at runtime. Really lovely to use, and would happily actually use it on applications as well. I mean, there's an Actix web server that's highly performant. It's probably one of the top tech and power benchmarks as well there. So yeah, looks really good.
Very good. And one last question just came in there. Any good example projects that you would recommend people look at? Anything they can build and play with and try out?
Oh, so example projects. One of the things I did just to get playing with it, and probably was just using something like Advent of Code before Christmas, so that where so I was just tackling all the problems there, working through them, and then it was great because the community, as you were doing those day on day, you would be able to see other people's implementations. They had a subreddit running as well, where people were able to talk about how they tried things and attacked things from different standpoints. Probably the only thing I can think of, the Rust book itself, as I say, will go and bring you through building a simple HTTP server as well. So there's some projects in there which you can sort of go through step by step.
Excellent. Brilliant. Listen, thank you so much. That was amazing. We will bring you back at the end for any questions. But for now, if I can dismiss you, very good. And if I can ask Chris to come on.
Hello.
Excellent. And I think your talk will your talk will continue on even. Very nice from Richard. So that the floor is yours. Yeah.
Hopefully, yeah. Okay. Yes, Sam. Okay, so hey, I'm Chris. I've been using and sort of following the development of Rust for it must be like 8 or 9 years at this point, since it was only on the mailing list from Mozilla and the IRC channels and stuff there, all the infrastructure that's now been replaced by more modern alternatives. So I've been at this for a long time. I've used it professionally for sort of various small tasks at a few of my previous roles, and for the past 5 months I've been working on it full time at my new role at LogDNA. So it's something I'm really enthusiastic about. This talk is going to be hopefully by the end of it you'll have a rough idea of how you can take Rust and add it into your existing code bases. It's brilliant for it, and hopefully you'll see that by the end of this talk. So I'm sure you've all heard the hype all over the internet for the past 5 or 6 years. You've listened to Richard's talk. You've seen the benchmarks, like you can see on the left-hand side here from the benchmarks game. Rust is one of the top 3 performing languages in the language benchmarks game, which has seen hundreds and hundreds of hours of optimization per language and per benchmark in them. So it's right up there with C and C++. It's as expressive as they come, as Richard was saying there. It's got all the functional abstractions. It's got nice trait-based polymorphism, and yet it's still memory safe by default. It's got all the power of sort of C and C++ and none of the syssegv. So you don't have to worry about it crashing in production, which is nice. These days, Rust isn't even only used by Mozilla, where it originally came from. It's used and it's backed by huge organizations like AWS, Cloudflare, Microsoft, even Google use it for OS dev. It's fast, safe, concurrent, and if I'm going for the full hype, it's the greatest leap forward in software engineering since Bell Labs gave Dennis Ritchie at PDP-11. So now I've given you all that. You're thinking, oh, this is brilliant. And you turn around and you look at your existing code base, say it's C++, You know, you need the performance, you need the control, but you just can't afford the debugging time. It's prohibitively difficult to eliminate all the like memory unsafety and the random data races and crashes, and those things are a very high percentage of the security vulnerabilities in modern web browsers. Like this is the graph for Chrome from Google's Project Zero blog. Most of the issues you can see here, use after freeze, other memory unsafety, those make up the vast majority of the security problems that Chrome has run into over the years. Microsoft has very similar stats. It's one of the reasons that they're investing quite heavily in Rust. Or maybe you're not using C++ or C, maybe you're just, you're running out of sticks of RAM to feed your app's runtime. Maybe you just need something a little bit more sort of lean, sleek, just slightly less hungry for RAM. Or maybe not even that. Maybe you just have nothing more productive to do whilst you're waiting for your model to train. Whatever your existing code base, at this point, I hope you've decided, like the internet has foretold it. It's time. Stop feature dev, throw it all away, rewrite it in Rust. Okay, maybe not. But Rust is awesome. Really should be looking at it. It can help you in a lot of ways. So maybe something less extreme. Maybe not throw away absolutely everything and go and write it again, especially because historically rewrites are one of the riskiest things you can do. If you remember the sort of 15 years of a virtual monopoly from IE 5 through 7, that was contributed to by Netscape deciding not to compete for a while whilst they rewrote. But I need to rewrite some of it, whatever your code base is doing. Maybe it's not fit for purpose in something. It's grown beyond where it can handle the load. It's no longer extensible, or maybe it's just one of these issues. Maybe the current language has just too much runtime for what you need to use, or for what you need to use it for. Maybe you want to embed it in another language, but if your current language has a big VM required, or even just a garbage collector that requires initialization before you can call any functions, that doesn't integrate particularly nicely with other languages. Maybe your language is too slow. Maybe you're running Python or Ruby and you just need some small component of it to be a bit quicker. Maybe your language, or maybe your system's too memory hungry. Maybe there's you've got a big graph structure or something like that, and you're allocating thousands and thousands of nodes, and it's just absolutely eating up your RAM with all the overhead. Maybe it can't meet latency requirements if you've audio processing or your GC, something like that. Or maybe it's just like C++ and C. It's too prone to error for your safety critical or your security critical application. Or maybe you just have an old component and it doesn't play nicely with any of the other languages that you're currently using. Rust is an excellent candidate for any problem where it's anywhere on this list and some others outside it. So you don't want to do a complete rewrite because incredibly risky. So what about a piecewise rewrite? Maybe you want to, or maybe even you're just adding a new component and you know that the current language won't be able to do it well. Or maybe you just have a greenfield but you will need to integrate it with an existing project at some point down the line. Rust is perfect for this. So you pick a component, somewhere it will be useful. Find an interface or a seam or something if you are going to be rewriting the component. Having a bunch of tests around this is obviously very useful. And then you can do something like the following. So just to recap, now we have a seam. Once you don't just go off and rewrite your entire code base. It's not worth it. However, if you do have something where it is applicable, you now have a CN target to oxidize, and it's a problem that Rust can address well. So anywhere where not having a runtime is important. We're being cross-platform. So Rust doesn't need a VM to execute. It doesn't even need like a fat runtime. It doesn't like Go or Haskell or Camel, etc. When a Rust library starts, there's very little global environment that assumes to be present, and the core of the language assumes none at all. So you can actually use it for like OS dev down in like you can write an Arduino OS in it without there's no libc, there's no kernel. It can just target the bare metal. For cross-platform, answering Garth's questions earlier, Rust is truly cross-platform, well, at least for all platforms that LLVM supports, and hopefully in future, all platforms that GCC supports, because Rust leans on the LLVM backend. It can easily link with C or C++, compile with Clang or GCC, and even MSVC, which means it has true first-class compile support on Windows. It's natively compiled, so it generates exactly the same compile artifacts as C and C++, your .o files or your .obj files on Windows. So those can just be linked into your existing application. Now, none of that would be very useful if the stuff in those object files was different. But thankfully, or was different, and the C and C++ couldn't understand it. But thankfully, Rust exposes and trivially exposes C-compatible API and ABI, which I'll explain in a moment or two. And there's also a very large ecosystem of tools and libraries for making this foreign function calling convenient and easy and safe and reliable. Okay, so I'll go into these sort of one by one, not in any particular order. So Rust can expose a C-compatible API and ABI. What do I mean by that? So a bunch of things make up the C API and the C ABI. So one of the important things for Rust is that it can generate code which is laid out byte for byte identical to the way it would be in C. So for example, over here, we have the point struct in the Rust version up top. It has an X and a Y member. It's just a coordinates. They're both usize in Rust, which is the pointer size on your platform. That has exactly the same layout in memory as the C equivalent down below. So if you have a piece of C code with that header, or you have a piece of Rust with that, and you allocate or you create a point in either of them, you can pass that back and forward between them both, and it will just work. It takes into account padding, it takes into account all of the low-level stuff that you don't really want to deal with on a day-to-day basis, but Rust will handle it quite happily for you without any like byte level manipulation required. Other things that make up the C API and ABI are the calling conventions. So how does a function call get rendered down into assembly language? Rust can quite happily specify that its function calls will be rendered down into assembly language exactly the same way as C's are for a given platform. So different operating systems, different compilers, different configurations can have different calling conventions, and it's one of the big blockers for calling back and forth between the different libraries or different objects. So Rust has great support for managing that. It also gives you control over how the symbol names in your output binary, so your .o files or whatever, your dots, DLLs, your .sos, etc. It gives you control over the data that is output into those, so that you can make sure it lines up nicely with the what you're expecting from the other language. So for example, here we have this nomangle attribute, which tells the compiler not to change the name of the usePoint function whenever it's putting it into the binary. Normally, Rust would add a bunch of additional metadata to the symbol because it can, and it's very useful, but you can tell it not to, and that will allow it to be called by C. It also allows you to, via Cargo, the package manager in the build system, Rust also allows you to specify what types of output artifact you would like. So For example, the Java compiler will output jar files. Python's byte compiler outputs PYC files. GCC and Clang, etc., whenever they're compiling C and C++, will output .o or .a or .lib, etc. files according to your platform. There's generally two types there. There's dynamically linked objects, and there's the statically linked objects, or objects for static linking. Rust allows you to specify both of those. So here's a short snippet out of the cargo manifest for a Rust library, which you want to export essentially a DLL and a .lib from. There's also a couple of layers and categories of tooling, which make all of this a lot easier. Like, you don't really want to be dealing with just doing raw C bindings between your two applications all day. It gets tedious and it's error prone, and you have to drop into unsafe code, and it's generally not as nice as it could be. So thankfully, there's a whole lot of tooling has been developed around that. So sort of from the bottom up, there's binding generation code, or the binding generation projects. Like, for example, for C, there is an application called CBindGen, which will take your Rust code and generate C header files for you. For C++, there's an awesome project called CXX, which I'll look into, or I'll show an example of later on, which allows you to do calls between C++ and Rust using the native Rust and C++ types without having to drop down to a C API in your code. So it allows you to use high-level things like passing the Rust string type to C++, or operating on a C++ standard string a C++ standard string in Rust, and you can do that without copying or any of the horribleness that generally goes with that kind of transfer. So I'll show a couple of examples of the CBindGen and some of the other ones here. So given the input in the top box there, given that's valid Rust code, it will see that there is a struct defined with the C representation. It has those two fields, and it sees the function below, and it will generate a header file, the bottom block there, that you can just include straight into your C application. You don't have to write that manually. You don't have to do anything. You can do it. You can even automatically generate it by adding in a build script to your Rust application. So you create a build.rs file in the root of your application with the following in it, and it will create a bindings.h file based on the exported C API from your Rust code. So you don't have to worry about keeping these in sync. You don't have to do any of that work. CBindGen will do it for you. Then anything that's been any library created, like the cdylib or the DLL created by Cargo, when it compiles your code, can then trivially be loaded into another application by, say, Python's FFI, or via CGO, or if you're in .NET, you can use pinvoke. You just load it like you would any other C or C++ native library. Then there's also for C++, and this one's really cool. So it depends what your background is as to sort of whether you appreciate just how cool it is to go straight from C++ to another language using native types. But there's this brilliant library by one of the, it uses a lot of macros, and it's from one of the people in the Rust community who's really, really good at writing the macros. But all you do is attach this little CXX bridge annotation to a module, and it will go in and take that module and try and use it as a spec for C++ to Rust binding interface. So because C++ doesn't really have a stable ABI, and because with templates and generics and stuff like that, it's very hard to call from another language that isn't C++. And Rust has exactly the same things just because of the way it works. This project acts as a bridge between the two. So as you can see in this example, down in the unsafe extern C++ block, there's actually a function in there defined with Rust syntax because it's convenient, but there's a function in there that takes a ampersand stir, which is a native Rust string slice. And that's in this code you can see, or in this like spec, you can see that it's being passed to a C++ function, and whenever CXX goes off and generates the header files for C++ and generates the whatever it needs to do for Rust, it will create a compatible C++ header that you just have to fill in the implementation for. And then you can pass the types back and forward between the two without any overhead at all. It's great. There's no converting to C types. There's no copies, no serialization, deserialization. It all just works, sort of zero cost or very, very little cost. Then if you're trying to interact with something a bit higher level, you don't want to go through the C API, you're not using C++, you want to actually write an extension for whatever VM or interpreter you're using. There's a whole bunch of crates out there that allow you to do that. So for example, there's Rustler for Erlang, there's JNI bindings, there's a couple of different ways to do it for Node.js, depending what version you're on. There's a couple of ways to do it for Python, again, depending on your preference. There's several for Ruby, but I picked the one that looked most up to date. There's plenty for other languages as well. But these allow you to write Rust code that can be loaded by the interpreter that is expecting a C library to be loaded. And these provide nice bindings that will generate all the boilerplate for you. So for example, here's what's a module for Python written in Rust using the PyO3 library looks like. Again, with the macros, the little annotations up there. This allows you to basically make a DSL to create your Python native extension using Rust. And as you can see, it's not very much. If you've ever written a C extension for Python, you know that you have to manage passing around the Py objects. You have to incgraph and decgraph and all sorts of stuff to make sure that you're tracking the reference counts and things on it. This library does it all for you. You just, for example, all this code does is creates a Rust to Py module that contains a function called add1, which will take in your integer, add one to it, return it. And this will do that at native speed without any faffing around the place. It's really, really nice. I've used it quite extensively. There's the examples for Ruby and for Node.js and such are all quite similar to this. The Java one's a little bit more complicated, but it's a slightly lower level API. They're all much for muchness. It's creating a library or creating a binary with a C API that the interpreter can load and run, and it just works. It's brilliant. Actually packaging those up. If you have a C extension or a extension written in Rust for Python, you can package it up as a wheel. You can distribute it using the many Linux and whatever other formats, and it will just work across the different systems. You can upload it to PyPy. Like, your consumers don't have to have a Rust toolchain installed as long as they can download wheels for their platform. And same thing goes for Node.js and for Elixir. If there's a way to create a mix that will pull in the Rust code, build it, generate the library, and package it all up, so you don't have to worry about that. It's just, yeah, it's lovely. But there's still some other cases where okay, so you can easily call Rust from my language. However, what happens if I have more than one language? Or what happens if I'm trying to compile to more than one platform? I don't want to write multiple sets of FFI bindings. I don't really want to have a artifact for every single platform. Like with Python, I can just distribute a single source file and it runs on Windows and Linux and Mac, and wherever I put it, it's just a .py file or a wheel containing Python files. It runs everywhere. I don't want to have one of these for every single platform. Well, enter WebAssembly. So anyone who's seen any of my talks before, I end up digressing into WebAssembly awfully quickly anytime I talk about Rust, because they are like really, really well suited together. So for context, WebAssembly is a native execution platform, or sorry, it is a bytecode interpreter, bytecode JIT that is designed for the web. So it's designed to run inside a browser and run at near native execution speed. It's meant to be, and it's looking like it will be, the one execution platform to rule them all. So you don't need you won't need a Python interpreter, a JVM, a whatever else. Hopefully at some point we'll be able to compile them all down to WebAssembly. And even if that's not the default way to run them, you should be able to run everything on this single platform. And that's really cool. You can also run C and C++, or at least you can run WebAssembly that is the compiled version of a C or C++ or Rust program, which is really cool because it allows you to sandbox it. There's a whole bunch of really nice things going on. And it's also because it was originally developed as a C and C++ compilation target. It's perfectly suited for Rust because everything is laid out the same. So you have WebAssembly, and okay, cool, that's a thing that could run on every platform, but I want to call it from my own code. So that's where Wasmer comes in. So Wasmer enables super lightweight containers based on WebAssembly that can run anywhere. It essentially allows you to treat a WebAssembly file or a WebAssembly artifact as a cross-platform DLL or a cross-platform .so file. If you have some WebAssembly, you can just load it into Wasmer, and then there are bindings to pretty much every language that you can think of using for Wasmer already. So all you do is import the Wasmer package for your language, and you can load up the WebAssembly compiled Rust that you've previously generated. There's a nice package manager for it. It's great. It's nice and portable. There's still some limitations around exactly what it can do, but that's because WebAssembly is a fairly young project by the sort of general standard of things. So, quick example. Here's my standard Rust example, which is the incredibly performance-sensitive sum function, which takes two integers and adds them together and returns them. As you can see, this one's been tagged with the nomangle attribute so that we get an actual function called sum after it's been compiled, and we compile that using the Rust wasm target, and it will generate a sum.wasm file somewhere on your system. Once you have that, you should be able to, say from Python, just import the various Wasmer components, initialize a couple of things, and then, as you can see on the fourth line of non-commented text there, you just open the simple or whatever the file name is, read it in, read the bytes out of it, and the Wasmer engine will compile that and give you back an interface that you can call. So further on down there, you can see an instance of that module. You can grab the sum function that it exports, and you can call it. So this is Python code that is passing numbers to WebAssembly, or to WebAssembly runtime, running WebAssembly that was generated from Rust and returning a result. And as I said, near native execution speed. It's really cool. But so this is the Python one. I said it can be called from other languages. Well, here's the Go version. So this is like pretty much the same. It's just a lot more verbose because Go. But all you do here is you create a WebAssembly module based on the WebAssembly, the bytes from the simple.wasm file. You import the object, you create a new instance, or you import the module, you create a new instance of the module, and then down near the bottom, you grab the sum function, you call the sum function, and it returns 42. So this is this is from Go calling exactly the same WebAssembly as was used from Python. So now all you have to do is compile your Rust down to a single WebAssembly file, distribute that WebAssembly file using the package manager provided with Wasmer, and you can have that, you get back to that nice state where you have a single file that can be shipped around onto any platform, and it should just run. So thanks for bearing with me for all that. I think I'm just about at time. So my general conclusion, Rust is extremely powerful. It has, as you saw right back at the start, it's as fast as C, C++. It can communicate, or it can be called from other languages extremely easily. It's really easy to embed in your existing code because it doesn't have a runtime or a GC or anything like that. However, you don't need to rewrite the world in order to use it. You can just pick a small place that you think it would be appropriate. For example, at work, I've been looking at using it for a bunch of file system interaction, which Node isn't particularly great at. And also, whilst also using it full time as our log shipping agent because of the very, very high performance and low resource usage. There's a whole lot of tooling already available, and there's more coming every day. For example, there's the binding generation, etc., and CXX, and all those are improving day to day. They're expanding the API surface they cover. It's getting better, and it's already pretty good. And finally, WebAssembly is really cool just because you can actually run it everywhere. Not really that Rust related, but yeah. All right. Thanks very much. Any questions?
That was awesome. Thank you very much. Absolutely loving those slides, especially the zero head hammer. I thought that was brilliant. Although as a senior developer, my immediate instinct was, could you not just turn it sideways and hammer that way? So a few questions here. So first of all, any language features that you cannot use if you declare a function for export? So if I put on no mangle or extern C or whatever, does that disable anything I might want to use?
So it shouldn't really. The function parameters and the return type will have to be something that can be represented in C. So you can't use generics on that particular function. However, you can use a concrete type and wrap up a generic function, and that will allow you to call that no problem.
Yeah, cool. Are the generics reified out of interest?
That's Rust allows you to be explicit about it. So by default, I believe it's the same. Yes, so they would be. It employs monomorphization. So it's like C++ templates. Whenever you it basically makes a new copy of the code for every instance of the different generic.
Cool, brilliant, yeah. And then talking about C++, it's been a long time since I did C++, but I remember discovering with horror that C++ isn't even compatible with itself. Compilers then, So
it's got a bit better in recent years, but
yeah. So how on earth does that CXX tool work then? I mean, is it compiler specific, that the output that it produces?
So it assumes it creates a header file for C++. You can then go and fill in the implementation of that, and then you will compile both the Rust and the C++ with the same LVM and link across them, or with at least one that has a compatible API. So you should be able to compile the different objects and pull them together.
Cool, brilliant. Yeah. Yeah. And then are there any use cases where you can really see people doing, writing the front end in Python or Java or C or whatever, and then the back end in Rust?
So the front end in C. Mm-hmm. I'm not sure about the front end in C. The other ones, yes.
Yeah.
The other ones, yes, I can see that. Being able to share types between the two fairly trivially is it's a fairly big sell. That's one of the reasons that like Node ever came about in the first place, was being able to share code between the front and back end. With Rust, you can do that via the C API, or you can do it via the those FFI bindings. If I was going to do it, I'd probably use something like gRPC or something like that. That is less tied to the like actual compile time artifact, because I wouldn't like to. With the C API, it's not too bad because it should stay stable across versions, but I wouldn't want to be like messing about with a big endian front end and a little endian back end or something like that. Weirdness could ensue if you're not deliberately making sure byte orders and stuff are correct.
Yep, very good. And then speaking on behalf of people who used to do C++ and are very aware that it's changed in all kinds of deeply scary ways, do you think Rust will end up as a C++ replacement then?
I'm not sure it's going to end up replacing existing C++. It may replace it in certain places. So like, for example, in Firefox, where that's what it was designed for. It was they tried a couple of times to rewrite Firefox to be parallel and couldn't get it to work without like data races and problems, just because they couldn't keep all the complexity in their heads at once. So there's a couple of aborted attempts, I think, at that, and they went off and wrote Rust, and suddenly we now have Stylo and the other components of Firefox, which are heavily parallelized because Rust allows you to track that kind of information in the type system. So I think for certain use cases, yes. For places like gaming, maybe not so much. As things like CXX improve, I see it expanding into existing code bases, and I really see it as more of a C replacement than a C++ replacement.
Yep.
Cool. At least that is at the moment.
Brilliant. Excellent. Look, thank you so much. Time marches on, so I must dismiss you for now. And if I can call on Philip to do our third talk.
Hi, how's it going?
Over to you. Thank you so much.
Hi, thank you. My name is Philip, and I'm currently working for Embicosm, working on a new compiler for Rust. So something over the last maybe 2014, I started the project where I saw Rust come along. It was still at version 0.7-ish, and I started writing a GCC compiler. I'll explain a bit what that is in a second. And yeah, so I'm actually working on that full time right now, and you can see here on the slides there's a crab on the screen. This is actually the mascot for Rust. It's called Ferris the Crab, and you can see in its claw it's got an egg, and that's the logo for Godot. And I spent probably far too much time cropping the claw in half and layering on top, but it's just to demonstrate that Rust has grabbed onto GCC at this point. Move on, next slide. So yeah, this project is designed to be a full implementation of Rust on top of the GNU toolchain, and the GNU toolchain is something that was originally done back many years ago, before I was born, in fact. So it was originally released in 1987 by Richard Stallman, and I was born in 88. So it's quite funny. And if you go to Git and do git log and go to the very start of the history, you can actually see it's like almost like archaeology, like you're digging up the remnants of like a pyramid or something. But it's been going on for a long time. It's been one of the main compilers for system level languages this whole time. You know, for C and C++, it supports Fortran. It actually has support for D, Ada, and Golang as well. There's also a bin-utils package that goes alongside this, so that's your assemblers and your linkers, and also a debugger. So also the goal of this project is that eventually, given enough work and a lot of effort, that it will be accepted as a as mainline GCC. So whenever you download the GCC source code, you not only get all the existing front ends for all the other languages, you also get it for Rust as well. So the other part of that is that the goal isn't to rewrite the Rust standard library or anything like that. It'll be reusing the official standard library, and we also want to target the latest language version. So the minute using the Rust reference and as a goal for that for now, because Rust actually doesn't have like an official spec or anything like that yet. So that's one place that has been difficult, but there is more than enough documentation out there to move forward with that. So what is a front end? So this is maybe something that was touched on by Chris's talk, where about object codes and executables and so on. So we can see here Ferris the crab. So Rust goes in and we get GNU comes out at the very bottom right hand corner. So the bit that I'm working on is the Rust front end. So this is the first part of a compiler. Compiler is always generally broken down into three components. So you have your front end, which is responsible for your parsing the language, doing all the transformations required to give you a fully typed version of that, and pass it into the middle end. So LLVM and GC both have a middle end, which is where all the compiler optimizations occur, constant folding and so on go on there. But each of them, like LLVM has LLVM IR, and GC is called generic. They're similar in many ways and different in other ways. It's just an intermediate representation of what the actual source code is. So that includes location info for all the different constructs in your language, be it loops or conditional expressions. But generally in these intermediate representations, loops, for example, or conditional expressions are represented by labels and go-to statements. There's a lot of these high-level things are stripped out, because to make optimizations generic for any language, you can't really have language-specific constructs in there. Like generics are stripped out, so everything is flattened out is the term we would use a lot. So you can see Rust goes in, gets handled by this Rust front end, which we're working on. Middle end runs some optimizations on it. Then another representation comes out, and that's when your target specific backend operates on. That's where you get your assembly comes out. So compiler is responsible for generating the assembly. So this is what we're working on here. So, and a lot of the things that GC gives you is that you'll get like array bounds checking in the middle end. So Rust also has errors for, like, if you're trying to access array out of bounds. That's not something a front end can do. That's something that the middle ends and compilers give you. We get strict aliasing for pointers, or and so on. So like, why would you work on like this? I mean, it's a big project to think that you could write Rust from scratch in C++, which is interesting. So I'm actually writing C++ at the minute more than I write Rust, which is unfortunate. But my personal motivation back in like 2014, like I've always liked working on compilers. I did Google Summer of Code 2 years in a row working on a Python front end to learn a lot about compilers. I got mentored by Ian Lance Taylor through that. Also then worked for the Python Foundation on the third year of Google Summer Code writing GCC plugins for Python. So I have a lot of experience with playing with GCC. I really like the community that it has. And the other part of compilers is that it's hard. It's something satisfying about working on something that's hard. And not only that, is pure data structures work. I'm not worrying about connecting out to databases and hoping that thing will stay alive, or, I'm not really worried about things like that. It's about pure data structure work. Can you get it working? Can you do these transformations? Does that algorithm make sense? So for me, I just really like working on compilers. I've got experience in GC, but I've also got experience in LLVM. In previous experience, I've actually wrote backends for LLVM, such as the NanoCores project was an EU project, which was interesting because LLVM has a lot of good things about it. But I personally just like GCC. I think it's got a nice community. So one of the other interesting things for why you would work in this project is like generally if you ever look on websites like Phronix.com or something, they would have like benchmarks for GCC versus LLVM. So it's something that will be quite interesting. I think Rust will target GCC very, very well. And what will be the result of that, you'll end up seeing potentially very different optimizations are being run on this code at that point. So you'll see very different code sizes at the end. You'll see very different register allocation depending on the target you're tackling. Energy efficiency even is another one people talk about. There's different security features that'll be offered by each of the compilers as well. So what will the end result be like? I think it will be pretty interesting. And generally, system level languages like C and C++ have always been supported by GCC and LLVM. So I think it's an interesting project, and I think there is a lot of room there for people to want it. I mean, one thing that comes up quite a lot for me is people talking about porting to different operating systems. So Rust isn't maybe available on all the different Unix operating systems, and there's some targets that it's not there yet. It has got a lot of targets. The main targets people care about, Rust is there, but there are a lot of ones that people talking about. I've got emails about PowerPC. I'm not sure what the state of PowerPC is for Rust, but I've had emails, people asking me about what, letting them know when this thing will be ready so that you could port it to such and such a target. So like, yeah, I've started to touch on the benefits here. So benefits would be like, it's maybe a lofty target, but like the standardization of Rust, Rust doesn't actually have a spec in it. It's not much of a problem, but having multiple compilers does push for a standardization of the language. At the minute, the compiler, we're saying that if something doesn't work in GCC Rust the way it does in Rust C, then that's a bug with us, until we get to a point where we can actually compile the full test suite and so on. We're not really in a position to say that Rust has done something wrong. So that's the approach I'm taking at the minute. So the other part of that is that it will actually help bootstrapping the Rust C compiler. Rust C compiler generally depends on downloading previous versions of Rust because the Rust compiler is written in Rust to bootstrap itself. So actually having a separate implementation in GCC would make that a lot simpler. The reason I got to work on this project full time now is that I got contacted by Brad Spengler from GR Security and really referenced this paper about the idea of mixed binaries. So in the Linux kernel recently, it was announced that people will be allowed to write compiler drivers. We're able to write drivers in Linux in Rust, and so there's interesting security concerns with that. So in this paper, it describes mixed binaries. So if you mix like Go with C++ or Rust with C++ and so on, or C, given different compilers have different optimizations and so on. And in this particular example, Rust uses LLVM under the hood, and for most people, the kernel is built with GCC. And most compilers now offer a thing called link time optimization. And what happens there is all the object files involved in creating your artifact, be it a library or executable or so on, all get examined and make sure that everything resolves to something correctly. Or in this particular one, we're talking about is CFI, is it control flow integrity, so that whenever a function jumps to another function, we're making sure it definitely jumps to that function, because otherwise you might have like a redirection of execution exploit in there, so you could actually take over a program and so on. So, but if you then mix LLVM built Rust code with GCC built kernel code, then you won't be able to have the full link time optimization, because the link time optimizers in GCC and LLVM work differently. They're not compatible with each other. GCC can't link time optimize LLVM code and so on, and vice versa. There are other implementations of doing CFI, but there's similar problems as you go down the hood. So one of the real things here is that having a GCC built version would fix this problem. You also get reusable GCC plugins. So a lot of projects I've seen in Firefox and Linux kernel have GCC plugins to provide extra diagnostics on different parts of the IRs in GC, like such as register transfer language or the generic or Gimple trees and so on. We can inject code to do different things. So all those would end up being reusable because the front end will be outputting the generic IR, and at that point everything is shared. So yeah. We also get more backend support. GC does have more support for different backends and operating system, which I touched on earlier as well. One of the other questions I get is, why would you write it the way I'm writing? Because at the minute I'm writing this as a full C++ implementation of Rust, which is, it's a big project. There's a lot of work to that to get it right. And I have the goal to, make it on par at some point. Some people say, well, why not reuse the GC JIT interface? So GC also offers us a JIT interface. So you can actually, instead of writing it the way we are, Rust actually has multiple backends. So there's the CraneLift backend, which Chris touched upon for WebAssembly. It's a separate backend to Rust, so it's not using LLVM at that point. It's putting out WebAssembly. So what you could have done is wrote a JIT interface there, so it calls out the GCC code. But as far as I'm aware, cross-compilation isn't really supported that way yet, so that'll make it difficult, and it's still an alpha. Plus, it's not really what I would believe what people want. I don't really see why people would end up choosing Rust C minus GCC. I don't know why. I don't know. It's kind of it's definitely an approach that would be interesting, but it's not the one I believe is the right way forward. And then the other question, why not use mrustc? So mrustc is another project similar to ours, but it has a different goal. It has a goal to compile just the Rust compiler. It's not really concerned about getting all the optimizations in there yet. It's also the licensing isn't really compatible to reuse mrustc in GCC. And it also requires runtime type inferencing features. So, dynamic casts and so on in C++, which aren't really, and C++ 14 features in general aren't available to write code in GCC yet. So there's different problems there. It's definitely a really interesting project, and it looks really good. The other main option would be to reuse Rust C. So you could actually write the Rust front end in Rust in GCC, similar to the Ada front end, and reuse the MIR outputs. But it becomes a very difficult bootstrapping problem, because what version of if GCC releases version 10, what version of Rust is supported then, and so on. Plus, MIR is unstable. What level of testing would then be put on GCC to be sure that a release of GCC actually does support that version? Becomes a difficult problem. So to actually get a GCC version of Rust, I personally believe that the best way forward is to write the one from scratch. It's also easier to maintain a front end in C++ for GCC in general. So I'll maybe just give you a quick demo of stuff that's in here already and what it looks like. So I've got a couple of examples. So I've got a couple of examples in here. One of the things, the state of the compiler is we don't have macro expansion in yet. So unfortunately, I can't show you Hello World, because Hello World requires macro expansion and traits to be implemented, but we're not there yet. There's a lot of things to get working first. So well, I'll show you this one first. I'll just show you the example program. So this is one of the first main programs I was working on in the compiler the start of the year to get working correctly. So in Rust is a very complicated and very powerful type system. It's been touched on a couple of times, and we'll discuss it a little bit later. In Rust, you don't really have to type anything. So you can see that we're doing let x equals this constant, and we can see this constant is i32. But what you can also then do is, for example, this let's see, it's called a declaration first. So you can say, let's see, it's just some variable. And we would say c equals 1. Well, what is 1, and that means generally, like in C++, if you use the auto keyword, you always have to have a right-hand side initializer. You can't do that otherwise. And Go is similar. So this is a very different type system from the get-go. When you see something like this, it's on the second line. You could have written that way on down. Here's another example. You're saying D equals B. So then you're creating like a chain of variables which aren't typed. And so the type system has to handle this, even parameters. So parameter is set to a value, and parameters then used in this function. So it's not until a type is then what we call unified against another type as that then gets a proper type. And then and Rust uses what's called inference variables, which are exposed to the programmers, which I'll show you an example later on using inference variables. So I'll just show you what it's like to compile a program using this. So you can see here, people who have used GCC before will be kind of familiar here with some of these options. So invoking the compiler GCRS, -G gives us debug symbols, which has been a lot of work in to make sure all the debug symbols are passed down into the native binary or executable, whatever you're doing with it. Turning optimizations off, because these examples are kind of toy examples. If I turn optimizations on, the compiler is going to realize, well, this program doesn't really do anything. But I want optimizations turned off just so I can show you what it looks like. I've got frust-dump-all. This is a compiler driver specific option, which gives us different debug outputs, which be used for debugging. fdump-tree gimpel. This is one of the GC's intermediate representations, which you might find interesting to see. So if I compile this, so I'll specify I want to compile integer inference var and give it an output infer. If I do, -v might be interesting. So you can see there's a bunch of debug going on here. There's a lot of printf debug, which we're trying to strip out at the minute and use a logger at the minute. But you can see here that, it's realized there's some unused names. You can see it's invoked the assembler. You can see it's invoked a linker to give you an executable at the end. So we should be left with, we've got an executable here. So if I do file infer, it's a 64-bit executable. There's also these different debug outputs. So if I'll maybe just run the program. So one of the things, because I don't have print lines at the minute, it's hard to test programs. Sometimes it's nice to be able to have automated test suite to actually pick up, does this program output this, therefore it's correct. We don't have that yet. But one of the things we can do is we can run our programs in GDB now. So we can actually, start the program. We're in main. We can, print x. X is 10. You can keep going. So all that sort of works, which is another way we can test things, which is very useful at the minute. And so you can see here. This is what the output in, this is what GCC is working on right now. It sees that I've got a function test U32. This all looks very C-like, and that's kind of a nice baseline for all languages to work from. You can see because all of these variables were not marked as mutable, they're all const. They're also given the correct types. As you can see, they're all a mixture. Although integers default I32, this was not necessarily the case in this program because we were unifying against a parameter and a return type of a function test, which took an unsigned type. And so it's able to handle all those different cases. So that was one of the first things, getting type inferencing working correctly. So that was a fair bit of work, and I'll discuss a little bit how that works in a slide later on. Let's delete that. Let's look at another one. I'll maybe just show you one more. For instance, there is a generics one I've got here. This is something I've got working very recently. So generics in Rust are, you could say, similar to C++, but there's very different ways to invoke them. So you can see here, I've got a generic struct. It takes a type parameter t. So a is going to be whatever t is. So you can see in this first example, a2, we're telling that the parameter is of an i8. So that's an just like a char. just like a byte. Then we then making sure that when we access the actual field of A, we make sure and force the compiler to make sure this is an I8 because we specified it here. But then we can also say don't give the variable declaration a type, but then just infer it from here. So then we've done similarly, let's give it an I32 and the same thing. We can also in Rust not even bother giving it a type parameter. So we can actually just say here, set A to be 1.0, which defaults to be a float, and F32 as well. So it's quite powerful here that you don't actually have to do anything. And it's funny, this example where you don't specify a type is very similar to under the hood here, where you can actually just do give it an infer type. So underscore just means here infer this, but in theory that really just works the same as the one above. So yeah, let's see if this compiles. Okay, so a lot of unused names and so on, but we can see here. As you can see here in the GIMP output, GC is actually now being told here we're creating new structs because unlike languages like Java or Python or so on, templates could be implemented by reusing like JObject or PyObject under the hood. And when it comes to native languages like C and C++, you actually do have to create these versions of the structs and methods and so on. They actually are separate methods that are generated by the compiler. So there's a performance gain there, but there's also, it takes up more space. So there's a trade-off there, but I think it's a good trade-off. Yeah, so we can see that it's actually correctly inferred all the types throughout here. And we can also run it as well. So we can see going, and everything looks as it is. We can print our structs and we can see the types they are. We can access the fields and so on. So there's a lot of interesting things there. Some of the other things that we've got working on the compiler recently is, we've got methods. So we can create structs and give it an implementation. So we've got methods doing what we expect. We can also give proper receivers. So this is the first example of actually giving. If you create a struct, these are like static. These ones which don't have a self argument are like static functions, like you would get in other languages. But down at the bottom, you can see here some x takes self, which means it's a receiver of a struct. So that means it's like a method as you would expect. So there's quite a few things working already in the compiler, but there's a ways to go. So there's a lot of work to get that going. So feel like I might be getting close to time, but I'll just give a quick run through of how the compiler works. So in the front end, there's a few different passes in here. This was the best way I could think of getting the diagram on one page. So it kind of goes across and down and up and down. But so we get Rust comes in, there's Lexer, which produces a token stream. We get a parser, we get an abstract syntax tree, but then that goes into macro expansion, which isn't complete yet. Then it goes into name resolution. And so there's actually two parts to name resolution. Whenever we get macro expansion, there will actually be a name resolution before macro expansion, because there's macro expansion, or sorry, there's name resolution, and then there's name resolution late. A name resolution, the first pass is like a top level pass to look for all the top level macros so that later on, whenever macro expansion detects a macro invocation, we know where that macro is in the definition of where it is. So it can be expanded. Then name resolution late is about drilling into all of your structs and your methods and gathering up all the information required. Then it goes into an HIR lowering. So this is, I'm kind of copying a lot about how the actual Rust compiler works. It seems like the correct thing to do at this point. And that's about stripping out macros, for example. Macros don't exist at this point. We can also, like, all loops are turned into loop expressions. So while loops are just loops and so on. So there's a lot of different things that just get cleaned up and we don't have to worry about. So it creates a nice immutable data structure to work with, and also limits the amount of stuff we actually have to work on whenever there's less in there. Then there's type resolution. So type resolution is also responsible for doing method resolution as well, because you can't resolve methods until you've done your type resolution, because you don't know what type you're working with as the receiver until that point. Then we then send it to a generic backend. So it sounds weird, but in GC, the IR we're putting out is called generic. So we're sending it to a backend to output generic intermediate representation, and then send it off to GC, and then GC takes care of everything else for us at that point. So we get all the optimizations that we would usually expect. Not sure if we've got enough time to go through some of these, but I was going to discuss a little bit how name resolution works and how we build up some information here. But an interesting slide is actually this type resolution system was made by Roger Hendley, which he actually went to Queen's in 1961, which was kind of cool. And it's used in Rust and Haskell as far as I know. And the core idea is about unification of types. So an interesting case of this system is actually in this example here. You can see we've got a mutable variable x. We can then say, so that's just an inference variable. We don't know what it is. We'll hopefully get some more information later on. Then we could set it to be none. So at that point, we know it's an option of something. And so we now got the constraint of it's an option. But then when we say sum 1, 2, 3, then we know it's an option of some integral inference variable. So we know it's of some integer. So it's a very powerful system that builds up by unification of everything over time. So that's what I think. It's pretty complicated, but it actually is really really useful. Sometimes I wonder if it could even be applied against Python to see if you could type inference Python, but it'd be interesting if that's possible. Yeah, so that's talking a little bit about inference variables. Basically, you're creating up a chain of things involved. But yeah, future long-term projects. Currently, the compiler doesn't have a borrow checker. That's something that isn't really on the landscape right now. It's the last pass inside the official Rust compiler on its MIR intermediate representation. So I don't really see why we should work on a borrow checker until we've got the compiler working first. Until it can compile all of Rust, it'd be more hassle than it's worth to work on a borrow checker right now. Another problem is that in Rust, everything in its crate, which is all the source files, is all seen as a single compilation unit, which actually means compilation could be slow if you have a lot of files. But Rust is addressing this by something called incremental compilation. That's something I would like to do at some point, but you can't do incremental compilation until you've done query-based compilation, and that is something that is sort of in the compiler. So the idea of query-based is that everything is given an ID, and so everything can be looked up. So if you're doing incremental compilation, your compiler is actually outputting a bunch of data about the compilation of your program behind the scenes. And this is serialized and then loaded up again. So if you recompile something, you've changed a signature, a function, and how it's called, it'll load all this old information of your previous run, and it will then see what's changed and then recompile what was needed instead of recompiling everything. Another long-term project I would love to have, it's not something on the radar right now, but it's an idea to make this front-end code sort of separate from GC, to make it independent so that you could potentially retarget it for other compiler frameworks, which would be pretty interesting, I think. There's some weird and wonderful Rust syntax that I get sent sometimes. So like, there's some strange ones in here. Like this, zombie Jesus, this is called loop, while, return, if, return, match, return. Because everything in Rust is an expression, you can do this sort of thing. Return is at this point is just unit type, which is similar to void in other languages. Yeah, so you can do a lot of cool things, but then that also means you have a lot of weird syntax to also handle. In the end, all this will end up generating a bunch of returns in the type resolved HIR. So that's what will end up happening, but it's interesting to see it nonetheless. And you can also see here strange, let x equals bool equals return true. So you're trying to add return true into a variable, which is technically return true is a Boolean type, so that is assignable, but yeah. So I've been learning a lot through this whole thing. So Rust is a complex language, and one of the main things there's not enough test cases. There's never enough test cases, and one of the most useful test cases have been test cases which look for failures, because there's a lot of cases of code which shouldn't compile, bad type inferencing and so on. So that's something I need to keep working at, is adding more test cases and taking the time to just write a lot of test cases. But that's something that has been really useful. Using a tool called DailyGNU in GCC, which is really designed for this type of work. It's about DailyGNU is all about how do you get this code onto a system and how do you run this code, and that's kind of all it really cares about. It just goes ahead and does it. So it's kind of designed for compilers and so on. But it's pretty old-fashioned, and it's written in Tickle TK and so on, which I'm not very good at, because very hard to find much documentation out there on it. But another thing I'm doing is I have a blog, and I keep a developer diary on there. So every week, you'll see a weekly status report from me on the compiler and how things are going, and also a monthly status report. And it's actually quite nice to be able to go back on these and see how far you've come, which is quite motivating, and it's a nice thing to do. So here's some links. Here's the project's on GitHub. So it's GC Rust or rustgc.github.io. There's a GC Rust Twitter where I post the links to my status reports one. There's a Zulip server that Zulip gave us, which is really nice. It's also part of Google Summer of Code 2021. So there's some students who have already expressed interest in this. So if you're a student out there, feel free to apply and or contact me if you're interested in doing Google Summer Code, and I'll find you a project. But special thanks to Open Source Security Inc., Bradley Spengler, and Jeremy Bennett for making this year possible for me, and the GC steering committee, David Edelson, and everything has made this a really great year for me so far. Thanks. That's me.
Hi, that was absolutely brilliant. Thank you so much.
No
really
problem.
Enjoyed that. And it is amazing to see people volunteering to do stuff that we were forced to do whenever I entered the I remember being told in my first project, our linker is broken, so you'll have to hand mangle your function declaration. Nodding, pretending that I really understood precisely what that meant, looking it up afterwards. So brilliant. Just to correct you on one thing, 1988 was not 33 years ago, okay? The 80s were just yesterday, okay? Please tell me that's true, KLF will never die, so... So I had a bunch of questions, but you've answered most of them. I was going to ask about the best way if anybody wanted to get started with compilers and stuff, but you covered that. I was going to ask you about the different passes the compiler did, but you did that. There's one that you may have answered and I missed it. Is there a formal suite then of compiler tests for Rust that you can work against?
Yeah, so there is and there isn't. So there is the official Rust test suite. So that's something we can use, and it is really useful to actually go through, because sometimes when I'm writing tests, I'm a wee bit too nice to myself.
Oh, as do we all, yeah.
But the thing is, I can't then just take all of that test suite and add it to my project. So I can't, because it's different licenses, it's not compatible with GC. So I have to then go out of my way to do that, which is a bit of a pain. So I'm building up my own test suite as I go. Mm-hmm. So it's a game of two halves there.
Yep, brilliant. And then will error messages be considered first class? Are you taking a lot of time with those, making sure they're descriptive by design, avoiding cryptic errors, that kind of thing?
Yeah, we're trying our best there. There's a lot of error handling in there at the minute, but sometimes it's not as nice. It's not as nice as Rust as yet anyway. That's to be expected because it's early on. I mean, we're not even doing Hello World yet. But for instance, you'll get, like, if you get one type error, you'll get a cascade of all the rest of them later on. Just keep getting more and more errors depending on how big your program is. But that's something we do put a lot of work into. All the location info is there, so when you do get an error, it'll print you the line of code, a little thing underneath where the error started, and so on.
Cool, very good. I think the remaining questions were by your fellow presenters. So if I can ask everybody else to join at this stage, and that they can ask them to you directly. Great. So guys, just go for it.
Right. That was brilliant. That was really, really interesting. Thanks. The one question I had was, what do you think's going to be the most difficult language feature? Do you think it'll be the borrow checker or macros or like the async await transform, or where do you think the difficulty will be?
See, I started thinking, generics would be, that'd be fine. And then it took me about 2 weeks there of sweating, trying to figure out how to make this nice, because actually I spent a lot of time reading the Rust source code. So it has a thing called the substitution manager or substitution ref or something like that. But it's really cryptic to see how that actually works. And so at the minute, I'm trying to apply generics to impl blocks and add it to methods and so on. There's a lot of work there. But my real worry at the minute is traits. That's something because I've been given funding for a year. I want to try and use the funding to the best abilities I can, because I could spend time working on something like imports and visibility. That's kind of simple enough, or mangling. This is kind of low hanging fruit there. But getting on the traits, that's where my biggest unknown is. That's something I want to tackle this year. There's a lot of work in there to make sure everything is applying the traits correctly,
Can you do a talk then if you ever get to like lifetime parameters or these sort of things? How you get out of this set of generics would be amazing.
I know. See, like I'm parsing and maintaining all the lifetime parameters, but I'm not doing anything with them at the minute. So that's all for borrow checker someday.
Do you think there would ever be a point when you could sort of target like large public Rust libraries that are, say, held on crates, just to be able to say we're compiling Tokyo or anything like that? Or
yeah, once I get to the point where I can compile at least most of the official Rust test suite, that's when I'm going to start trying to compile other things. I reckon at that point, like there still won't be a borrow checker at that point. It's not something is a requirement to compile Rust. It just won't pick up problems. That's you'll lose out in the diagnostics there. But that's when I want to start doing that. I'm quite anxious to get going there, because I think a lot of progress has been made in the last few months. So it's exciting. There's contributors working on macro expansion for me in the background as well. So it's not something maybe something I'll get for free.
Just one last one. Do you think? So I know that there's work going on like libraryifying the existing Rust-C front end. Do you think you'd be able to use like Polonius or Chalk or any of those whenever they're more mature, or are there licensing problems there, or what?
Yeah, I mean, that's something I thought about at the start. I do worry that there'll be licensing problems potentially, because it's all Apache MIT, whereas to work on GC you actually do need to apply for copyright assignments. So I lose copyright to my code, but I get I do get my name's put on it. But that's part of the deal when you do work for the Free Software Foundation. So I worry that if you did go down that route, you would get very far, very quick, and it would be really, really brilliant. But then later on, be like, oh, well, we can't use this, which would be my worry. It's probably unlikely. But one of the things that's happened from them doing that amount of work is actually it's made the code easier to follow, and their documentation's got better, because sometimes you can go in the Rust reference and find bits and pieces, but actually until you delve into the code, of how that works, sometimes you miss implementation details.
Cool.
Brilliant. Excellent. Thank you so much. So we've gone past time. So just to say thank you so much indeed. That was 3 absolutely brilliant talks. Thank you so much. But if I can just dismiss you. Yeah. And just in closing to say thank you very much indeed for attending. And thanks as always to my co-organizers, Zara and Ryan. And Ryan couldn't be managing StreamYard in the background because of a teaching commitment. So Aaron was doing it on this particular occasion, and he's done an absolutely wonderful job. So thank you so much for that. So listen, thank you for attending this event. The next event, the Modern JVM Development Bash, we'll be releasing the details of that next week. So please stay tuned, and thank you very much again.